All right, so I did the other example in class, and I'm not going to repeat it here. I did a recording in, that one's going to be up and available to people this semester. I'm not sure if this video will get used in another semester, and if so, I probably would have shown that same example. I wanted to do one that has everything in the kitchen sink in this one problem. So I went ahead, this is an example, or a homework problem I should say, I did from, I think, spring of 2018. I might recirculate it at some point, but we'll see. So I created this problem because I wanted specifically to have as many different failure modes as possible, but I felt like students were overwhelmed by it. So let me talk my way through this to try to explain it. So we have two different plates. They have two different thicknesses, T1 and T2, and I set it up in a table here so that we would have things. One's 10 millimeters and one's 12 millimeters. So they look similar, but they're different. T1, plate 1 is actually thinner. They're also made out of two different materials, right? Where plate 1 is going to be made out of 1015 cold drawn. Plate 2 is out of 1030 hot rolled. Well, now what I should have done in hindsight is to flip these two things over and make the thinner one the stronger material and make the thicker one the weaker material, and then you would not have known right away where the failure mode was going to be. But I didn't do that. I also made because you could see there's two plates, so A1, I guess from what we're seeing, is actually going to be this plate right here. So A1 actually goes with plate 2, and then A2 would actually be for plate 1. All right, so that's another thing where I wish I had figured that out a little ahead of time. And I gave B right here so that we were able to figure out what this distance is that's going to be between there. All right, so I made A1 10 and I made A2 12, and I think at least I got that one right. Okay, yeah, so the A2 is a larger one, but it's a thinner plate, so that's going to help out here. And I put 50,000 newtons on it, and I gave a bolt specification. It's a metric 10 millimeter bolt. So I start off with shear of the bolts. I have 3 bolts, so there's 3. They take the pi over 4 times the diameter of the bolts squared. So now I have the shear area of the bolts. Looking up at the material, it's going to be the bolt material that I looked up from table 8.1 out of this ISO 5.8. That's going to give me my strength, my yield strength, and then I multiply it by 0.577, and I have my shear yield strength. And so then I have, so I'm going to use that down here. And then the shear stress, I should have pointed out, was going to be 50,000 divided by that area. I get 212.2, and so I get a safety factor of 1.14 when I divide that strength by that stress. And this is a big time apples to apples thing, right? We would talk about apples to apples. Oh man, this is definitely the apples to apples of all time, because we really want to be able to get the correct area for the loading condition. We want to put on the correct load too in some cases. We want to get, so we find out the right kind of stress, and then we figure out the right kind of strength for the material. So they have to match up so that we get a ratio, and we could judge what the safety factor is. Now the tension of the plate, because we have two different plates, we have to do plate 1 and plate 2. So it's going to be the width of it minus the number of bolts times the bolt diameter times the thickness of plate 1. And we end up with this area. So then we end up with this stress, 250 megapascals. And so we use the yield strength that we find from plate 1, which is 320. And that stress, we get 1.28. So it looks like the bolts and shear will fail before the tension of the plate 1. And then tension of plate 2, we have the area is a similar thing, but we're going to have a different thickness right here, right? So that everything's the same as the one above, except that we had a thicker plate. So we have a larger area, so we have a lower stress, but our strength is lower. Okay. So so we do have some competition right there. So we'll see that we have 1.25, right? So this actually turns out to be worse than that one. I think I got that right. Now let's take a look at shear rip out of the plate, right? So we use this A1 minus D over 2. So this is really going to be that X value we were talking about. It's to the front of the bolt and to the edge right here. So that's going to be the X right here. The same thing is, that's going to be for the underside. It's actually over here for the one that's above on the top. But it's really from there to there, right? It's the projection of that edge. And we take, and there's going to be 3 of them, and there's 2, right? So there's actually a total of 6 of these areas that are resisting. It's a little weird looking right there. Of course, it doesn't actually going to work that way. But that's all right. We're following through here just as a means of comparison. We get an area, and we're able to figure out what the shear is going to be right there of it trying to shear away through there. We find that now we use the shear yield, right? So we're going to use that von Mises times the yield strength to find the shear yield strength. And so we take in that ratio and we get 1.11. So that looks like it's got a potential for failure here. For plate 2, all the same things, except that we have a different A2 and we have a different thickness right here. So we have a area right here, and we actually end up with a lower stress. And then we also have, interestingly enough, that it almost comes out to an even number right there. I guess it does. When we get to the 0.577 times plate 2's yield strength, we end up with a shear yield strength of 150. So then we end up with a safety factor 1.51. So he looks like he might be okay. Then we have bearing. We have going to have 4 different bearing safety factors. I know you actually have to really think about this. We have two different thicknesses, so there's going to be 2 different stresses. And one of the stresses is going to be applied to the top plate and the bolt, and the other stress is going to be the bottom plate and the bolt. And they both of those stresses are going to be the same thing. So on the bolts on plate 1 are going to be the thickness of plate 1 times the diameter right there. It's the projected area times the number, right? So there's going to be 1, 2, 3 of these things. And we have this area, and this is going to be a compressive thing, so we should really even put a compression next to it. And then we just take that the strength of the this is going to be on the bolts, right? So we take the bolt strength first and take the ratio, and this is the safety factor we have. We use the same stress as above, but now that stress equal and opposite is going to be on the plate by the bolts. And so we're using that same 166, but we're using it with a different strength. So there you go right there. And if this were the kind of material that had a different strength in compression as tension, we might need to adjust for that too, because this is a compressive stress. Now we have bearing of the bolts by plate 2. The difference here is that we're going to have a different plate thickness as the one up here, up above. And we end up with a different area, so we have a different stress. In terms of a less stress, that plate has a different... now this is on the bolts, right? It should be on the bolts. I think I miswrote this. This is actually a typographical error. I'm almost certain right there. That right there should be 420. And I think if you do the math, it probably is going to work out that way, but I just wrote it down the wrong. I used to do these by hand, and then I would make so many mistakes, and I think, that this would be the correct value if we were to do it that way, with that value. So I caught yet another one of my mistakes. And then we use the same stress up here, and then we use the 260 for the other plate, and we get 1.87. And then, almost there. Now, these plates, they could bend, right? Looking at this figure right here, the force is not in line with that force. So there is a possibility even that it could, bend. And like I like to draw them kind of like up this way right here, right? So, and then we draw the bolt as part of this right here, and we could put the bolt head right in there. So the pieces are bending. And so we get the moment right here is going to be, I determined that it was going to be 0.011. That's going to be inside this plate, inside this bolt right there. How did I decide to do that? Oh, okay, I guess I took the average. That's what I did. That's going to be the point about which the thing moves. So I took the average thickness, and I think it should be yeah, okay, so the average thickness of the thing to figure out about where it's going to go. And so I took a moment about there of and get 550 Newton meters, and then I had the moment of inertia. They're going to be different for the different plates. And also C is going to be 1/2 of the thickness of each of the plates, right? So we get bending stress of 1,650 megapascals. That's a lot. And we take it to the yield strength of the plate, and we get 0.19. So boy, that's really likely. I think that thing just failed. And then we could do the same thing for plate 2. We get a different I and different C. And then we do MC over I. We get a lower stress, and we compare it to the yield strength of that other plate, and we get 0.23. So here's a summary, and this is what there's where a lot of things. A lot of times I will tell people to put these in order, actually, because then you can go and you can go like this will happen, so this will happen first, then this. But we saw from the example piece right here, right? The example that had failed that I had shown before. Let's see. Oh, I guess I turned the camera's still there. There it goes. We saw that this thing failed in bending, right? It failed in bending, and then they kept pulling it, and then it failed in tension, right there, tensile of the member. So bear that in mind. Bear that in mind. No, that's not a pun. This doesn't count as a pun. So get this stupid thing out of the way here. I'll minimize it. Put this back in together. And just talking through the rest of these. I think after these bending is going to happen, this guy, this shear rip out of plate 1, that thing's obviously way too close to the edge. That's what that tells us. The next, interestingly enough, I think is going to be the shear of the bolts. And then we're going to have, the tension of the plate 2, tension of the plate 1. And then it's kind of a moot point because, all these other things failed. But we could have shear rip out of plate 2 could happen. So that was not nearly as bad in terms of being close to the edge. Then we can start arguing about what the next ones are. Bearing of the plate. We have bearing of the plate 1. And then some of the other bolt things could take place. So this is a really big example that covers all the ground. I don't think I left out any of the different failure modes that we cover really right here. So I figured I would add this in as an example instead of the previous ones that I had in the note packet. So hopefully this will help you in completing assignments, but also in doing exams, because the exam can have stuff that isn't on the homework. So maybe this is sort of something that those who actually came to the very end of this video will be able to appreciate. So let's see. And as a consolation prize for those of you, let's see, I gotta push this up first. Then I can take it off. And now I can put it back on. All right, there you go. It just likes to do that right there, doesn't it? All right, so I don't know if it's a consolation prize. I didn't think I think I probably have already shown this guitar, but I have it out and I didn't want to go running around there in the dark. I turn the lights off so it's dark behind me, and I didn't comb my hair. Look at that. It's grooming optional, isn't it? Grooming optional. Yeah, that's disgusting. Yeah. That's okay. I was a sailor. They would only have to take a shower there if you're all covered in oil, right? Smells worse in the engine room than you ever smell. So what the hell do you care? That's just a terrible attitude. You're not a sailor anymore. You shouldn't think in those terms. Yeah. Let's do something evil. No, maybe? I don't know. It's a little loud. How about a dual rectifier? This is supposed to be dual high gain. This is supposed to be a dual rectifier, right? That's not high gain. This is high gain. Wow, listen to the fuzz. Trick is to take your palm and you hold it down at the edge right here, so like you get these. I like these little harmonics right here that you're doing. Like a harmonic, for those who forgot their vibration class, is the vibrational modes that could take place, like that are existing all at the same time. Because a string vibrating has tons, maybe thousands, I don't know how many frequencies that are going on at the same time. There's the main tonal one that gives its name, that usually gives the name, but there's like broken down ones. Like there's twice the frequency, obviously, that's in there, and you can hear that twice the frequency by getting rid of the fundamental. And you can get rid of the fundamental by just barely tapping. So there's the note there, right here. There's the A string, and there's the fundamental. Right there's the fundamental being dampened out. So that's called, we call it a harmonic, or a natural harmonic. And it also and so what you're thinking about is that's like a jump rope, right? And you're pushing down on the jump rope, so you don't hear the jump rope, but you do hear the sine wave that has a node right there at the center of the jump rope, because that's not being interfered with. So that's right there at the center, and that happens to be at the 12th fret. Now the same thing, you could hear a similar one at the quarter spot, right? So now you're kind of damping out the big jump rope, but you're also getting the top of the sine wave. So now you can also do the 1/3 mark, and the 1/3 mark is kind of getting rid of I guess everything. It's 1/3 right here. It's at the 7th fret. And when you put on a lot of gain, you can start hearing some of the in-between ones. Like there's one like here at 4 that's kind of hard to hear and hard to get to go. There's like one in. There's one at 3. There's like one at 1.5. And you'll notice that they repeat, like. So there's one at 9. It's the same one at 4, because you're dampening out the same tops of the crests of all of them, right? But you can also achieve some of them by like dragging your hand back here. Now you can also get harmonics we call them artificial harmonics by well, some people take the fat of their thumb and just let it drag onto their, like here's the picking the note, but here's artificial. It's called artificial harmonic, and I also, when I first learned it, I would actually drag this right here. Just touching this part of the fingernail right onto the string. They're actually a lot easier to use when you have humbuckers and a high gain onto the thing. So there you go, artificial harmonics and all the different things that you'd want to know about playing harmonics and natural harmonics. And it was right here buried at the end of this video. So there you go. Thank you. Have a good day. Turn the video off. Stop watching. What are you doing? 21 minutes? I'm not going to even call it 21 minutes. Not really 21 minutes. But anyway.